All right, thank you. Yeah. So myself and Dr. Justin Nagan will just speak a little bit about synchronization of wireless nodes. Yeah, in this I'll pass on. So I know we're in the industry session, but I suppose it's because I try to do work that relates to industry. Maybe it looks a bit technical, but you know, one of the big challenges we have with structural health monitoring is large structures. Westgate Bridge is obviously, you know, super large. Stadia, any of these kind of structures that are absolutely critical for safety, for society's functioning. We really do want to be in a place where we can monitor them. And of course, the problem with such large structures is that you end up with a situation like this, where you've got a few kilometers of cabling to do. And of course, the likes of, you know, the Westgate or the MCG, they're not going to say, yeah, no worries, we'll close it for a couple of weeks while you lay out a few kilometers of cabling. It's just not going to happen, right? So at best, you might get a night, maybe a weekend if you're super, super lucky, where you have access to the structure. And so wiring is probably not a solution, right? Wired system, unless it's already built into the structure or you got some other special cases. So definitely, you know, and here's just some more examples of wiring. And of course, this is exposed and potentially subject to vandalism and lots of problems like that. So, you know, wireless sensor networks are really attractive from this point of view of avoiding this wiring problem. But the fundamental problem with wireless sensor networks is synchronization. So yeah, sorry, here's some of the wireless sensor networks that we've got. This is a product from the US called Resensus. You know, not sponsored by the Maranton, but it's just been really useful for us because we get to go up into one place, we put the sensor up, we put the node up, and when I say go up into one place, it's, you know, accessing a lot of these places is one of the fundamental challenges of getting these sensors in. So the fact that I don't have to run wiring means that I don't have to have the underbridge unit drive along the length of the bridge as I try to pin up some wiring, right? I get to park it in one place, install as many sensors as I can along the access line that the underbridge unit gives me. And you know, I get to kind of move the unit then to maybe 2 or 3 places on the structure, and that's it. And that leads to efficiency, and it means my install is done in one night and not, you know, 3 or 4 days when it's a wired solution. So these are, you know, wireless is super attractive for lots and lots of reasons. But for these long structures, then of course wireless is really what we're thinking of, because if we're going to do something like the Westgate, you know, overnight, can I get in a ute and just plop down some cases that magically do the sensing? You know, that'd be really attractive if we could do that, and I don't have to do any wiring. And so in one night, I could get a modal identification on a very large structure, right? So that's the kind of the idea. That's the goal. Can we achieve this? But as I say, the fundamental challenge is time synchronization. Now you can see the satellite there, and you say, "Oh yeah, that's easy. Just use some GPS." It turns out it's a little bit trickier than that. Yeah. Why is synchronization so important? Well, because if you don't have accurate time synchronization, your modal identifications will be inaccurate. And this is just an example of a simply supported beam where we've got just artificially introduced some time lag in the individual nodes in this, and you can see what happens. So the first mode is identified pretty well. Now you need to remember what your theoretical mode should be here, but you can see that the second and third modes are absolutely wild because of this lack of time synchronization in there. So how do we synchronize these wireless systems? That's the real challenge. So I'm going to pass over to Justin just to go through the next 2 sections then.
Okay. So left and right. Thank you, Colin. So Colin thought I would be the right person next to discuss a bit about the insights of what we do here, what our team has done here after many years of being out in the field, working with wireless monitoring and to give you an insight of what synchronization challenges are out there in terms of a practical approach point of view. So now, building on the idea that we want to have quick sensing, we have a node that we can just put on the bridge and then sensing. If we put multiple nodes together, we need to synchronize them. But however, what happens? The first big challenge is communication blackout. So, what happens? Most protocols communicate between the nodes using certain synchronization protocol. But what happens if their communication is lost? What happens if there's a communication blackout here? So to assist the explanation a little bit, here's a chart showing just the timestamp difference from a DAQ, from a sensor node and the GPS. What happens is over time you got this thing called clock drift. Your timestamp will drift because of the nature of the hardware. The computer tends to run at a different frequency over time. Now, what happens with this communication blackout? It worsens all these drifts, and in between the time period where you don't have communications, you can't identify what's the clock skew, and that's a big issue in terms of practical point of view of synchronization. Now, the second big culprit in causing synchronization is temperature. So some of or most of you may know that if your sensor is working at a different temperature, your clock drift or your synchronization error will be a bit different. So here's just a few examples. One from our test here, we showed that this test here has 2.5 microseconds of clock drift, and if we increase the temperature, that clock drift or the error goes up even further. So just to wrap up is saying that synchronization is really affected by temperature of our nodes. Building on what Colin just said, so if we put a sensor node on a big structure, one outside exposed to sun and one inside the bridge, which is probably cooler, you get different synchronization, different timestamps, and you need to synchronize these two. Really, the case here. And so the next bit is just what we try to achieve here at Monash. We have been very practical in a practical approach. We've tried to develop the idea of having a sensor node that we can deploy on site, being very, very prompt, and a sensor node that is autonomous and independent here. So these are just some of the characteristics of the independent sensor nodes. You want to be, like Colin said, you want to bring it on site. You can put it on the spot within 1 hour or two, and then start measuring for over a weekend or an hour or over a week. So we identified a few issues with the synchronization nodes, and here in Monash we try to understand or to improve upon this kind of current protocols that what they identified earlier, the synchronization challenges here. So in terms of synchronization capabilities, we try to, well, these are a few things that we did. We just do a counter, we interpolate. We want to interpolate in between those GPS blackouts that you saw earlier, and then on top of that, we want to try to apply a temperature drift model. This may seem a bit advanced, but that's why we take it on our hands. We try to build our own sensor to test all this synchronization. So here is just a sensor node that we have. We build it off just a DAQ that we have in the lab. It's just a National Instrument DAQ. Hook up with some modules with GPS module antenna to do the synchronization at the start. So we use GPS here to synchronize all the nodes that we have. So 1 node of 6 nodes and so forth. All this we try to package it in a very compact waterproof case, and is self-powered. So we try to make it independent, self-powered, and autonomous. So as you can see here, we can just bring it on site and to put it where you want in a big structure, and we can monitor it immediately once we start acquiring the data. Again, like what Colin said, the synchronization is the issue here. So a little bit of insight what we do with this is in regards to temperature, we have developed some a bit of an intuitive cork temperature prediction model to help estimate cork drift, because cork drift is affected by temperature. So here is just a chart of a little bit of what we did with our temperature model. We did a bit of studies on how this kind of synchronization error will affect your mode shape predictions. So as you can, if I flip between these two charts here, if I have if I have a little bit of time skew error in one of the nodes here, so particularly the fifth data point here, sixth data point, you know, you get a very big error in our mode shapes here. So that just skews, or that just distort a lot of your algorithm that comes after with, like assessments or damage detection algorithms. A little bit, maybe this is a bit advanced, but we're just trying to quantify here what the time synchronization error would do to each mode shape here. So it's just a chart showing that, okay, if I have this much time drift in my sensor, our mode shape will just, our mode shape MAC model shape criteria will just go deep down, yeah. And with some limited time, with our design that we have here, we've also did some real testing. So what we did, we put to test our design that we saw earlier, and with a wire system. This is just a disassembled case that you just saw. We just, for the sake of setup, and we matched them properly with like a 6-hour test, and this is just some of the results, and they work very well in terms of synchronization. Once we start up the system, comparing it with the wire system and the case, the independent sensor node here. And with that, that's all my part. I'll just pass on back to Colin.
Oh, give me that, Jan. Thanks, Justin. See, the trick there is to give Justin all the hard slides. But look, the goal here is a full characterization of the temperature clock drift relationship, as well as the thermodynamic properties of the sensor node itself, because when you know those properties and you've got those characterized and you have a relationship between clock drift and temperature, you have a much better way of interpolating and correcting for time drift when you have a GPS, a synchronization blackout. Yeah, so what this means is that, you know, we're getting really close to super accurate synchronization between nodes that are wireless, which means that we can cost effectively monitor very large structures without needing to go out there and wire everything. So yeah, that's the goal. I think it's a practical goal, but it needs a little bit of research behind it. John, yes. So yeah, this is what it looks like, but yeah, we get out there. Thank you very much. I think that's everything. Yeah, thanks.
Thank you, Colin.